Assalamu alaikum. Today we will discuss definition of continuum, then deformation, and then derivation for strain tensor. Continuum mechanics. Continuum mechanics, basically it is the branch of mechanics in which materials are treated as continuous. They should be continuous. Material are treated as continuous is known as continuum mechanics. Continuum is a matter in which we ignore the fine structure. What is a fine structure? Fine structure is the structure of any object in microscopic level. So we ignore that microscopic level in structure. In microscopic level structure, you can see that there are gaps among the atoms. And when we ignore that structure, that fine structure, so it means that we are ignoring the gaps, that we are supposing that there is no gap among the atoms of the particle of the materials. It is also noting that for a continuum, there are not only infinitely many particles but within each and every neighborhood of particle there are infinitely many other particles. This is what I was saying, that there is no gap among the particles. So mass will be continuously distributed throughout the whole volume. A continuum is formulated mathematically in terms of continuous functions, representing the properties of many microscopic objects forming the actual material. So for continuum we have continuous functions, because we are supposing that we have continuity. So the functions which will represent the properties are also continuous functions. So in notion of continuum, we describe the deformation and forces experienced by a deformable body in terms of stress and strain within the continuum. Deformation. So deformation is only possible for an elastic body. So when you deform a body in an elastic body, and that deformation will be dealt in terms of strain tensor, and the forces experienced by that deformable body, that elastic body, will be dealt in terms of strain within that continuum. And also the concept of continuum allows us to consider materials in such a way that their descriptive functions are continuous and differentiable. So it means that concept which we will use for the continuum, and when we are using continuum, this thing allowing us to consider all the functions as continuous and differentiable. So in particular, we will define stress at a given point, which will enable us to apply the calculus to the study of forces within the continuum, because we are supposing the continuity and differentiability, so we can apply the calculus on the force within the continuum. Moreover, what is deformation, that how can you define the deformation, that change in the position of particles of body, change in the position of the particles of the body. You have particles and you have body, and body contains the particles, and there are positions of the particles. When you apply the external forces, the position of the particles will be changed within the continuum. That if you have particle P with certain position, then when you apply the force, then position of that particle will be changed from P to another. Position of that particle P will be changed from the given position to some another position within the continuum. If this happens, then we will say that deformation occurs. And we also say after deformation, that body we also say that the body is said to be strained. That body has undergone strain. Then we will say that body as strained. So within this strain, there is stress which opposes the deformation to restore the original shape of the body. That when you remove the external force, then there is a force which will restore the original shape of the body, and that is known as stress. It is also oppose the deformation. We shall discuss only infinitesimal strain. Infinitesimal means that we will deal with only small level deformation. Relationship between stress and strain is mutual dependence. That stress depends upon strain and strain depends upon stress. That if there is strain, then stress must be there, and if there is stress, strain must be there. And it is basically the intrinsic concept of the elasticity theory. Now the strain tensor. That how can we derive the mathematical expression for strain tensor? Let us suppose a body having a particular arrangement at some reference time t0. This is at the time t0. Now it changes to another configuration, another arrangement at time t. Now this is with respect to time t. Now let us draw the origin here. Consider the point P here. So P of t0, that we are considering here time t, not here is time t. Consider a material point P undergoes a displacement u. Material point P here, this is the position of this point P with respect to origin. Now this point will change to P of t here. Here it is t0, and here it will be t, because this is at the time t. This configuration is with respect to time t. So the point will be also at time t. So with respect to displacement vector, with respect to displacement u, this u will be function of this x and time. So that now after this displacement, this point P will arrive at this position P. Its position will be denoted by this small x. So we can write this small x as x plus this u of x comma t. we will write this as function 1, equation number 1. Now consider also a neighboring point Q here. This will reach here. Here it is time t naught, here it will be time t. So its new position will be small x plus dx, small dx. Now this new will be equal to x plus dx plus this displacement u of x plus dx. So this can be said as 2. Now from 1 and 2 we can write this, simply take the difference of 1 and 2. You have this thing. Now if you remember the gradient of vector u, gradient of any vector, here the vector is u, then we can write from 3 as, remember that definition of gradient of any vector function. This value will be equal to, all this difference will be equal to gradient of u, which is applying on this dx. Now this is equation number 4. This gradient of u is the second order tensor. We know that. We know this thing. Second order tensor are known as displacement gradient, because u is the displacement vector. So to this we are saying that this is the displacement gradient. The matrix of this displacement gradient with respect to any rectangular Cartesian coordinates, this and this is this. This is the matrix form of displacement gradient. Now do the example 3.7.1 by yourself. Now we can write above equation, which is number 4, as take the dx common. Here we can write I plus identity plus gradient of u into dx. See, this is any matrix F, where F is this. Now we will operate the transpose of this F on both sides. Multiply these. We have these, as we are supposing that we are dealing with infinitesimal deformation, so it means that components of displacement vector and their partial derivatives are small. So it further tells us that the absolute value of the every component of this, so every component of this will be product of components, the product of partial derivatives of displacement vector u. So is a small quantity of higher order than those of the components of this. We know that components are small, and when you take the product they will become more smaller. So when you will compare the components of this product with this, then they will be more smaller than this, so you can neglect those. Because if you have 1 by 2 and 1 by 3, 1 by 3, 2 is less than 1, 1 by 3 is less than 1, and when you will take the product of 1 by 2 and 1 by 3, it will be 1 by 6 less than 1, and 1 by 6 is less than 1 by 2, and also 1 by 6 is less than 1 by 3. So product of smaller numbers become more smaller. So we can write this approximation. This thing can be written as this, where S is this, which is basically the symmetric part of gradient of u. Symmetric part of gradient of u. We see this tensor as infinitesimal strain tensor. This is what? This is the infinitesimal strain tensor, and this is basically, this is the symmetric tensor, and it is coming from the gradient of displacement, which is tensor. Basically this is tensor, this is the symmetric part of the tensor. This is the strain tensor. It means that strain tensor is a symmetric tensor. So it can also be noted that strain tensor is symmetric and it is second order, because you can see that this is second order, and this will also be second order tensor. So for rectangular Cartesian coordinate system, components of strain tensor will be in this form. It has 9 components, so you can write these 9 components as S11 will be partial u1 partial x1 plus partial u1 partial x1, 2 times 2 will be cancelled out, and partial u1 partial x1, S22 partial u2 partial x2, S33 partial u3 partial x3, and S12 1 by 2 partial u1 partial x2 plus partial u2 partial x1, and S13 partial u1 partial x3 plus partial u3 partial x1. This is S21, and we are saying that this is symmetric, so S21 will be equal to S12. S23 1 by 2 partial u2 partial x3 plus partial u3 partial x2. So it is S31. So due to symmetry, S13 will be S31, and due to symmetry, S23 will be S32, and this is S33. This is the form of the strain tensor matrix in Cartesian coordinates, where u1, u2, u3 are the components of displacement vector u, through which P is transforming from one configuration to another configuration, T0 to T1. First configuration is with respect to time T0, and second with respect to time T, and P is moving from configuration at T0 to configuration at T1, T, through displacement vector u. So these are the components of that u. This is what. So in cylindrical coordinates, these all components can be written as this. Now you have to obtain this matrix for cylindrical coordinates. In your previous lecture, I have asked you to find all the expressions like gradient of scalar function, gradient of vector function, divergence of vector function, divergence of tensor, curl of vector in terms of cylindrical coordinates. So using all the information about the cylindrical coordinates, you have to find this matrix E in terms of cylindrical coordinates. Now it's up to you that whether you do it or not. Today's lecture is a little bit theoretical from the start, so listen it carefully. Also you can consult from the book, which I have also recommended in our class, Introduction to Continuum Mechanics. Also any book of the Continuum, any other book of the Continuum Mechanics. Maybe you have Sham's outline for the Continuum Mechanics, so also consult that to understand all the theory. Thank you so much. Allah Hafiz.